Did I?
Oh, before we begin, um, let's just postpone the homework that is due tonight to tomorrow night, because we are not meeting tomorrow anyway, right? So tonight or tomorrow night doesn't matter. The homework number 8, right? I mean, like, if you are ready already, you can just hand it in to me right now. Otherwise, like, tomorrow night is fine, because a few of you requested it. All right. So now, is there any question before I begin the lecture? Is everything okay? All right. So let me begin chapter 4. Now that we know what a random variable is, we have basically 2 main branches for random variable. One is discrete and one is continuous, right? And then actually, if you are given one random variable, you can just generate, like some function of that random variable as well, and you can just go on and so on and so forth. And we also talk about John, whatever you call it, John, what do we call it? John distribution, right? So now the next concept is about expected value of a variable. What do I mean by that? So now let's say that, like if I have some random variable x right here, with, like some, whatever you call it, frequency function, let's say px right here, or little f of x, then the same, little p of x or little f of x, then I'm going to define the expected value for this random variable x right here this way. I'm going to sum over I of xi times pxi. Okay? For discrete random variable, I'm going to define it like that. So now, like, you might ask yourself, what does that mean? What does that measure? Well, think of it like a center of mass. A center of mass. You are given whatever you call it, probability frequency function right here, and then you want to find the center of mass, for example. Right? Sometimes this one right here is also referred to as mean as well, because like you are calculating in a way, the mean of it. Right? So this one is exactly the measurement for the mean. Okay? Or center of mass if you wish. Alright? And now, if it is a continuous random variable, what do you think I'm going to define it as? This thing right here, if it is, this one right here is when it is, how do you say, discrete right here. If it is continuous, what do you think that the analogous of it is going to be? The analogy of it. The integral from where to where? Like whatever, from negative infinity to infinity, for example, of what? X of I multiplied by the density function, and then you integrate it, right? So this is f of x right here, the x. Right? Can you see that? Maybe I should draw a picture right here for you to see what this one measures right here. Let's say that you have 3 things right here. This thing is right here is with probability x1 right here, and this one another from x2 right here is with probability of x2 right here, and this one is like x3 right here with like frequency function x3 right here. And then what do you do right here? You're going to multiply the probability of x1 right here with, like x1. That's the location, and you add with this one and with that one. It's like you are calculating the center of mass right here. Okay, that's what it measures. Right? So here, I'm going to put it right here for you to see. If you are given a random variable x, how do you compute the expected value of it? Well, like we said before, right there, if it is discrete, you're going to just multiply the outcome xi right there with the frequency function, right? And then sum everything together. And if it is continuous, well, you just integrate x multiplied by the density function over the interval that you're looking at. And of course, you might run into the situation that this integral right here is infinite, right? Why not? When you integrate something, it might be infinite, right? In that case, your expected outcome is going to be undefined. All right? So, therefore, the backtrack a little bit, the correct way to define the expected value is that for discrete, it's going to be this, provided that the sum is finite. And if it is continuous, then it's going to be that, provided that the integral right then is finite. Is that clear? Right? Okay. Actually, you know, it's stronger than that right here. You need to actually calculate the absolute value of it. Right here, if it is finite, then you say that the expected value is going to be defined that way. You see what I mean? Are you familiar with conditional convergence and absolute convergence from calculus? Yeah?
Yeah.
Give me a series that converges absolutely 1 over n squared, for example, the summation of 1 over n squared, right? Converges absolutely. So therefore it converges, you know, like conditionally and converges in general. However, you know, like sometimes, you know, like the series right there might converge conditionally, but not absolutely. Is everybody clear what I'm talking about? Give me a series that converges conditionally, but not absolutely. No? Like the summation of, let's say, minus 1 raised to the n over 1, multiplied by 1 over n. Can you see that one? It's going to alternate, right? Can you see that? So therefore the sum of it is going to be finite. However, if you take the absolute value around it, then you cancel the negative one. You cancel the oscillation. So therefore it doesn't converge absolutely. Is that clear? Right? Okay, but you know, like in short, just calculate it out. Okay? If it's finite, then the expected value is that. If it's not, then the expected value is not defined. How about that? Then we don't have to get into the weird area of absolute convergence and conditional convergence. Right? Is that okay? So, therefore, I'm going to define the expected value to be this, or this thing right here. When it's discrete, when it's continuous, when the summation or the integral right there finite. Alright? Is that okay? Good. So now, let's compute a few things. So, for example, the Bernoulli trial. Let's compute the expected value for the Bernoulli trial. Now, for Bernoulli distribution, how do you think of Bernoulli distribution? What is it? It's discrete, okay, but what? It's going to have just two outcomes, right? Either, you know, you flip a coin, it's going to be head or tail. And each one is with, you know, like probability, for example, this one is with probability p, then the other guy is 1 minus p, correct? So therefore, for the Bernoulli trial, usually we just write it as what? P to the x times 1 minus p to the 1 minus x. Remember that? Right? So for example, if x is 0, then what do you have? P to the 0 is 1. Right? And what is 1 minus p? Oh, it's just 1 minus p. To the 1 minus x. To the first power. So it's going to be p times 1 minus p. Right? Is that clear? So now, how do I compute the expected value for the Bernoulli thing. For example, this one is what I'm looking at right here. I'm trying to calculate the expected value for the Bernoulli trial. How do I do that? Exactly, so I'm going to do the sum right here, correct? Over I, and remember I, you have only two outcomes, 0 or 1, right? So I'm going to sum right here from I equal to 0 to 1 of x, right? And then p to the x times 1 minus p to the 1 minus x, because this thing right here, p1 minus p to the x, 1 minus p to the 1 minus x, that's the, whatever you call it, the frequency function, the f of x right there, right? Okay, so now you just have to sum it. Is everybody clear what I'm saying? And using this thing right here, expected value, to try to compute the expected value for Bernoulli trial. And remember, the Bernoulli trial, the f of x right here is exactly this function right here, p to the x, 1 minus p to the 1 minus x, right? So therefore, I just have to sum x right here multiplied by f of x, and then sum them. You have two outcomes, x equal to 0, x equal to 1, right? Okay, so you just plug in the formula. You have right here x equal to 0, so 0, p to the 0, 1 minus p to the first, plus x is 1, so you have 1 right here, p to the first, 1 minus p to the 0, that's p, the expected value for the Bernoulli trial right there, the Bernoulli distribution is just p. Okay? So now, how about
Dr. Nguyen?
Yes.
This is Debbie from Salt Lake.
Okay.
What would happen in a situation like the binomial trials where...
I'm going to do it in a minute. I'm going to try to compute them all for you right now. You are just a few steps ahead of me right now, Debbie. Okay? So now, let's say that if x is a geometric distribution, how do I compute the expected value for it? Okay? So now, what is the geometric distribution? Yes. So therefore, this thing right here, remember that. Let me just write it down right here. I think we denoted like p of x equal to k, something like that, right? Is equal to what right here? No, this is geometric. I'm thinking about binomial. Geometric is what? 1 minus, yes. So what is that? 1, yes. This one right here is going to be 1 minus p to the k minus 1 times p, right? Where k right there is the number of trials that we have to do until we get the first success, right? So remember that. And this thing right here is nothing but what the function f, little f right there is, right? Remember? Right here. This is this guy right here, okay? So how about I write f of x right here, of x if you wish. X equal to, just f right there. And now, how do I compute the expected value? It is defined to be what? You have to sum over everything, right? Remember right here, let me turn it over so that you can see it. This is this. Right? Sum over everything. And remember, over here, my xi right there is what? Is k. Right? My xi is k. And k goes from where to where? For the geometric distribution, it goes from 1 to infinity. Remember that? Yeah? So therefore, just put everything together. I'm going to have summation k equal to 1 to infinity. Of what? Of x, which is k now, right? xi right there is k. And then f of xi, which is what? This guy right here. Right? So I'm going to have what? K and then p, 1 minus p to the k minus 1. Is everybody with me so far? I didn't do anything, I just plugged it in the formula. Remember that in order for us to compute the expected value, we have to sum over just, xi times f of xi, another word, right? The formula right here. Xi times f of xi, sum everything. Okay, over all the I. So of course over here xi is k. And f of xi is this function right here. And k is from 1 to infinity. So now we just have to sum it. Now it's just technical kind of thing right here. So let's think about it. P right here is independent of everything, of k. Can I print it up front? Right? So I'm going to have P right here, summation of k equal to 1 to infinity of k right here, 1 minus p to the k minus 1. Right? So far so good? I probably have to use this thing from calculus. Now, store this one there for a minute. Look at the technical aside right here. I'm going to recall some fact from calculus. Namely, if you have, let's say, a function f of, or let's not use f, let's say g of y right here, equal to, let's say, y to the n, then the derivative of it is what? Then dg dy is what? Is n y to the n minus 1, right? Right? So with that in mind, back to this thing right here, this function right here, okay? If I let say look at this one, look at 1 minus p right here. 1 minus p is going to be the complement of it, so I'm going to call it q, right? So let's say look at this thing right here equal to q, and this thing is, let's say, to the k minus 1. This is q to the k minus 1. Agree? I didn't do anything so far. Okay? If I set 1 minus p right there to be the other complement, the other probability, let's call it q, then 1 minus p to the k minus 1 is nothing but q to the k minus 1. Now if I take the derivative of this thing, what do I get? Derivative with respect to q of the function qk minus 1, what do I get? Or actually, why don't I just put k right here first? Ignore that minus 1, just k right here. What is the derivative of this thing? K times q to the k minus 1. Agreed? Can you see that exactly this animal right here? K times q to the k minus 1. Right? So another word.
So is it k minus 1, or is it no longer k minus 1 and now it's just k?
This is k. Let's just say this is k, and this is k right here. Right? If I take the derivative of this one will be what? If I take the derivative of dq right here, of q to the k, it will be k q to the k minus 1. Correct? Right? So therefore, can you see that the thing that I circle right here is nothing but the derivative of q to the k? That's what I'm trying to say. Right? Good. So therefore, hence, back to our problem, the expected value right here is equal to p multiplied by the sum k equal to 1 to infinity. And can I write the thing that I circled right there as what? The derivative of q to the k. Great? Right? And now I'm going to, how do you say it? Exchange the order of the summation and the derivative. Okay? So this thing right here is going to be p times dq, the derivative right here of the summation k equal to 1 to infinity of q to the k. Agreed? Yeah? And now, what is this sum? What is that sum? That is the, whatever you call it, the geometric series, except that it's missing the first term, correct? Missing the k equal to 0. So what do you do in that case? Add and subtract, for example. So let's look at, before I take the derivative, let's look at the sum right here from k equal to 1 to infinity. What is that sum? Come on. If I have the sum right here, k equal to 0 to infinity of q to the k, then what do I have? This thing right here is, by definition, is 1 over 1 minus q. Agreed? Yeah? Over here, my sum starts from 1. So what does that mean? I'm missing 1. Right? So over here, if I start from 1, can I just say that this is going to be this thing and then what? Minus 1? Is that okay?
Right.
If I have k equal to 1 to infinity of q to the k, it's just 1 over 1 minus q minus z, the term k equal to 0, right? And q to the 0 is what? Is 1. So why don't I just write 1 right there? Is everybody happy with that? Okay. So therefore, this thing is equal to p, and then the derivative with respect to q right here of what? Of the function that I just found out right here, namely 1 over 1 minus q minus 1. By the way, can we simplify that nasty looking thing? Oh, just leave it there. It's okay. Right? Are you with me on this? And now, all you have to do is take the
Dr.
derivative.
Nguyen,
Yes?
could you just stop for a second so we can catch up with notes? Thank you.
Sure. Okay, so now, can we take the derivative of this? Exactly. This is p, and then the derivative of the thing in the parenthesis with respect to q. Derivative of 1 with respect to q is 0, so it gets cancelled. Good. And then derivative of 1 over 1 minus q is what? What is the derivative of that?
Minus 1 over 1 minus q square.
Okay, so derivative with respect to q right here is, I'm going to pick up a minus, correct? So I'm going to have, put the minus out here, and then multiply by 1 divided by what? 1 minus q, the whole thing squared. Agreed? Very good. Okay. Why did I do this one? This thing right here, did I do it right? How come I'm missing a term q right here? There should be a q.
Because the minus 1
Oh, okay,
takes
that's
the
what
q.
cancel. Okay, okay. So this one is going to give me this, right? Alright, and now what is this? 1 minus q is what? Is p. Right? Remember 1 minus p, q is p, so you have what? Minus p over p squared. So this one is minus p. Wait a second, where did I pick up that minus from? It should be there. There should be that minus right there. What's going on? Q is
q plus 1.
No, p plus q is 1, so therefore 1 minus q is p. That is correct. And then this thing is p squared right here, so this one is that. There should be a minus. Where did my minus come from? 1 minus p to the k, I take the derivative, it's this thing, so I put it there. This thing is this, so derivative of this thing q to the k is this. So therefore, this is
Because you have 1 minus q to the negative 1, you take the derivative, so you times by negative 1 drops negative 2.
Oh, that's to take care of this minus right here. There you go. Because I forgot to multiply derivative of the thing inside, which is negative 1. Okay, there you go. Thank you. So that's all. Alright? Don't get scared by the calculation. Nothing is straightforward right there. Right? Okay, so that's how I take the expected value. It's just, is it 1 over p?
Yeah.
Thank you. P over p squared is 1 over p, not p, not p. All right. So now, how about expected value for the exponential distribution? How do I do it? Okay, first of all, tell me what the function f of x is. Little f of x is what? Lambda e to the minus lambda x, correct? When x is bigger than or equal to 0, otherwise it's going to be 0. Yeah? Now I have to calculate the expected value for it. Now, this thing right here is not it's not discrete, right? So instead of summing of xi, f of xi, I'm going to do what? The integral of xi times f of xi. Right? So therefore, this one is going to be what? The expected value for that random variable is going to be integral. Can I just do it from 0 to infinity?
Yes.
Yeah? Because from negative infinity to infinity, the other one will kill it off, the x right here. So let me do it just from 0 to infinity of what? X times this guy. So you just have lambda times x times e to the minus lambda x dx. See how easy that is? Okay, that's how you compute the expected value. Did I do this thing, or you think you can handle this? You can just, for example, print out the lambda, because it's just a constant, and then you integrate this thing by integration by part. Right? Okay? If nobody say anything, I'm going to assume that you can do it yourself. You want to see it or not? It's easy, right? You can just do integration.
See it.
Yeah? I'm sorry?
See it.
Okay, so you...
Yeah, can we run through it just one time?
I'm sorry?
They want to see.
You want to see it? All right. So let's see that do integration by parts. I'm going to do u dv, right? So for that, I'm going to let u equal to what? X, for example. And my dv is going to be e to the minus lambda x dx. So my du right here will be the x. And my v right here will be what? E to the minus lambda x divided by minus lambda, correct? Okay? So now, I have lambda outside here, and then it's going to be uv, so this is u times v there, so I have x times this, so there's a minus, I'm going to put it up front right here, minus x times e to the minus lambda x divided by lambda, that's uv, minus integral of v du, v is this with the minus sign, so I'm going to put this one as a plus, and then I'm going to print out the 1 over lambda, and then v du, so it's going to be e to the minus lambda x right here, du is dx. Okay, so it's that. And now equal to, let me integrate this one first, and then I'm going to evaluate everything at once. So now, can I cancel the lambda, lambda, and lambda everywhere here? And then I'm going to get what? Minus x e to the minus lambda x plus the integral from 0 to infinity of e to the minus lambda x dx. And you know that that integral is nothing but what? Minus, I'm going to put the minus right here. And this is e to the minus lambda x over lambda right here, right? And now I'm going to evaluate everything from 0 to infinity. Now, let's do it. When x is infinity, e to the what? Negative infinity is 0, right? And then, unfortunately, over here you have x is infinity, so you have, in a way, like 0 times infinity. Which one is going to win out? Well, that is one of the indeterminate form. You have to use L'Hopital's rule. Or you can just quickly think about it. Right here, x is what? A polynomial. And x right here grows like a polynomial, and exponential function right here, in that case, they're exponentially fast, so the exponential function is going to win out, right? If you do the L'Hopital's rule, you will see that. So therefore, actually this one, if you put infinity in here, this one will be 0. Okay? And then the next one right here is minus. So this is 0 minus 1. 0 as well, so 0 minus 0. Okay? That's the upper limit. And then the lower limit. So now minus the lower limit. I'm going to put 0 in. 0 is 0. Right? Times 1 is 0. So that's gone. So this is 0. Minus, what is this? E to the 0 is 1. So it's 1 over lambda. So at the end, I'm going to have just 1 over lambda. That's the expected value for the polynomial distribution. Alright? And now is the question that I think Debbie asked me a few minutes ago. How about the expected value for binomial distribution? Right? Well, how do I do it? Again, this thing is what? Okay? This one is continuous or discrete? It's continuous, correct? So I integrated, and over here the binomial distribution is from negative infinity to infinity. Unfortunately, so I have to use the whole thing. I cannot cut it off from 0 to infinity. And now what? X times the whatever frequency function for the binomial distribution
Normal
is.
distribution, right?
I'm sorry?
It's a normal distribution.
Yeah, it's a normal distribution. What did I say?
Binomial.
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 I mean normal distribution. Okay. Sorry. Okay. So it's this. Okay. And now what else? What is the density function for the normal distribution? 1 over, what is it? Sigma times square root 2 pi. And then e to the minus x, I think minus mu, right? The whole thing square over, is it 2 sigma square? Okay. And then this is the x. There you go. Now you have to integrate that horrible looking function. Well, you know by now that this thing right here is the trouble term right here. So why don't I just do a change of variable to make it look better, right? And you know that the transformation that does the job is z equal to whatever x minus mu over sigma, right? So I'm going to let z equal to x minus mu over sigma. Then that means that whenever I see the x, I can replace it by what? Sigma dz. Okay, good. So now equal to, and over here the limit for z, is it still negative infinity to infinity? Yes. Right? Because mu and sigma, they are, how do you say it? Constant. There's some numbers. So infinity minus some number is still infinity, right?
Can you move that down a little bit?
Down? Okay. So this thing, integral, is still from negative infinity to infinity. And then, well, why don't I print out the 1 over square root right there, so it looks nicer. Square root of 2 pi times sigma right here. I'm going to print it up front. It's that. Now, when I see x, what do I replace it by? Well, over here, that means that z sigma is equal to x minus mu, right? So therefore, that means that whenever I see x, I better replace it by z sigma plus mu. Agreed? Right here.
Couldn't it just be like negative 1/2 z squared?
No, I mean, like, remember, there is an x right here.
Oh.
Right? So I have to replace that x by z sigma plus mu. Okay? So therefore, I have this one is sigma times z plus mu, that's for x. And now this thing is going to be e to the what? Minus z squared over 2. Okay, good. So it's going to be z squared over 2. Right? And then whenever I see the x, I'm going to replace it by sigma dz. Aha, now you see sigma and sigma cancel each other out. So therefore, I'm going to have basically this thing right here. So I'm going to split it up like 1 over square root of 2 pi times integral from negative infinity to infinity of, there is still a sigma for this guy. So therefore, I'm going to have sigma z times e to the minus z squared over 2 dz, and then plus, now there is a mu right here, which is a constant. I can print it out, so I have mu over square root of 2 pi integral from negative infinity to infinity of e to the minus v squared over 2 dz. Yeah? Okay? And now, this thing right here, the integral, I just circle right there, excluding the mu. That integration should give you 1, because it's a standard normal distribution. Okay? Or you can, this is the extra credit problem that I showed you. I asked you to do on the exam. Okay? You can show that that thing right there is square root of 2 pi. And by the way, I'm going to post the solution online today, so you will be able to see that that thing that I circle is exactly 1. Alright? So therefore, this thing right here is just going to be 1 times mu. Agreed? Now all I have to do is try to find out what this horrible looking thing right here is. Okay? So now, let's do it aside right here. Just look at this thing here. Alright? So, ignore the square root of 2 pi as well. Just look at this thing. This is z e to the minus z squared over 2 dz. Okay? Ignore the sigma and then square root of 2 over pi, because they are all constant. I don't care. If I know how to integrate this integral, I just multiply by sigma divided by square root of 2 pi. I get it. So now, how do I integrate that thing? By parts. Right? You can do that. Or I will tell you a little observation right here. Look at this function. Look at the function inside. Before I do that, let's just play this amusing game right here. If I have f of x.
Sorry, Dr. Nguyen?
Yes.
Sorry, we haven't quite finished those notes. If you
Not
could-
yet, not
yeah,
yet.
thank
I'm going
you.
to try to show you how to compute this thing. Alright? But before I compute it, I show you how to compute this thing right here. Let me just make a little observation with you right here, and then you will see this thing right here right away. Okay? Let's say that if you have a function f of x equal to x, okay, and then you integrate it over, let's say, from negative 10 to 10 right here, of x dx, what do you get? Anybody? This thing is x squared over 2, evaluate from negative 10 to 10. Agreed? What is that?
0.
Can you see that it's 0? Yeah? Now, if you, let's say, that if you integrate, by the way, there is nothing special about negative 10 and 10. I may as well put it from negative L to L right here, where L can be whatever. Like L could be a million. And then this thing right here is just the upper, right here limit is negative, is a million. Down here is negative a million. It's still 0. Can you see that? And now if I have integral from minus L to L of x to the third dx, what do I have? It's x to the 4th over 4, correct? And then this one evaluate from negative L to L. What do you have? Again, L to the 4th divided by 4, and then minus L to the 4 over 4, it's 0. Can you see that? Oops, I'm sorry. Yes. Can you see that? And now, actually, that observation that tells you something. What's the common thing about a function x and x to the third and so on and so forth? X to the 5th or x to the 7th? They are all odd functions, correct? Right? And when you integrate an odd function, what do you get? An even function. And of course, if you evaluate an even function from negative L to L, you're going to get 0. Can you see that? So the moral of the story that I just told you right here is what? If you integrate an arc function over a symmetric interval, you always get 0. Can you see that? Listen carefully right here. I am not claiming that integrating an arc function gives you 0 all the time. No. An arc function over symmetric interval, it's always 0. Another way to see it is this. An arc function is what? It means that whatever you have down here, you have it exactly up here. Correct? Reflection, it's symmetric over the origin. Correct? So right now, remember that integral of a function from A to B, what does that mean? The area under the curve. Correct? Arc function right here, if you integrate over symmetric interval from negative L to L, the area over here is exactly the area over there. They cancel each other out. Is that clear? Right? So keep that in mind whenever you have an arc function, you integrate it over a symmetric interval, it's always 0. By the way, with that token right there, if you integrate an even function over a symmetric interval, what can you do?
2 times 0 to...
Exactly.
You have a...
You just, if over a symmetric interval from negative L to L, right? If you want to integrate an even function, you might as well cut the interval into half, namely from 0 to L, and integrate that function, and then you double the answer. Why? Because it's exactly this. Even function, it means that whatever you have over here is exactly over there, symmetric over the y-axis. So therefore, if you do it over a symmetric interval, the area over here is exactly the area over here. So you might as well cut the interval in half and double it. Now, with that in mind, back to this problem. What kind of animal is that guy? Is it odd or even function?
Odd function.
It is an odd function because e to the minus z squared over 2, it is an even function. Correct? And z right there is an odd function. The product of an odd function and an even function is an odd function. Okay? Be careful right here. If you have numbers, odd times even is even. Right? Numbers. 2 times 3 is 6. Right? But over here, we're not talking about numbers. We are talking about function. Okay? You can prove it, but this is not just one line, 30 seconds. I don't have time to do it now. Alright? You can prove that an even function times an odd function is an odd function. So therefore, that animal right there is an odd function. You integrate over symmetric interval of an odd function, what do you get? 0. Because of the observation that we just made right there. Alright? So without doing any calculation, if you know that fact right there, you know right away that this thing is 0. Is that clear now? So therefore, now we can finish this problem. This thing is exactly 0 plus what? Mu times 1, which is mu. So therefore, thus back to our problem right here, expected value is exactly mu. Is that okay? Right? And then you can do all of them. Whatever the distribution that I give you. Right? You can just, if it is continuous, you integrate from negative infinity to infinity of x times the density function right there, the f. And if it is discrete, you just sum over xi times the frequency function, pxi on fxi, and then you have it. Alright? So now, the next topic that I want to talk about is the variance. Okay? First, let me define what it is first, and then I will tell you why do we care about it. In other words, what does it measure? The variance. Because we know that the expected value is nothing but the mean or the center of mass, for example. Now, the variance. Okay? The variance of x is defined to be this. Oh, by the way, Did I make this comment? Yeah, the expected value, sometimes they write it as mu. Okay? The expected value, just the notation shorthand, they write it as mu, which is the mean as well. The expected value is the mean value. They're the same. So now that we know how to define the mean or the expected value, mu, right? Now to define the variance, you're going to first look at the difference between x and the expected value that you just computed, right? So you form x minus mu sub x right there, and then you square that thing, and then you compute the expected value of that square thing. Alright? So is that clear? Right? So in a way, basically, if it is a discrete continuous, then right here you will just have xi minus the expected value right there, the mean, and then you square it, and then you multiply with f of x right here, the frequency function, and then you sum it. Can you see that the difference between this and the expected value is what? Tell me. The expected value will be what? Expected value of x is just xi times f of xi, correct? And then you sum over I. Over here, you still have f of xi right here, but instead of having xi right here, you will replace it by xi minus mu, the whole thing squared. Basically, that's the definition of the expected value of this thing right here. Is that clear? Yeah? Okay. And now, how about the other version for the continuous one? Well, just what you expect. You integrated x minus mu sub x squared and sub x dx. Alright? And now I'm going to tell you what that one means. Okay? The variance right here, basically, it just measures how things are going to get distributed, spread out around the mean value. Alright? How things are going to spread out, distributed around the mean value. That's what it is. In other words, you just like compute, you want to see how the expected value is going to be different from the one that you observe. Basically, that's what it means right here. Okay? I know that a few of you, we have a few graduate students in here as well, so I also want to give you another way to think of this. Can you see that this one is nothing but the expected value of the least square problem? The difference right there. In other words, you just calculate the derivative. You think about it, the expected of the expected. Right? So in a way, you can think of it like you are measuring the concavity of some function. The second derivative, if you wish, how things are going to turn. Okay? Now, never mind. So, that's what it is. And now, if you have the variance, by the way, the variance is usually denoted as sigma squared. Okay? Whatever you compute right there, in a minute I'm going to try to compute a few of them out for you explicitly. Okay? So, whatever you have for the variance right there, it's sigma squared. Okay? So, remember, sigma is what? Is the standard deviation. So in other words, when you calculate the variance after that, you take the square root of it, you get the standard deviation. And now everything connects, you see, because standard deviation means what? You measure how things are going to be away from the mean value. Exactly the notion that I told you a minute ago. Alright? Good. Let me come back to this in a minute. Remind me this one, okay? Because in practice, you don't use this formula right here to calculate the variance of a variable. Instead, you use this thing right here, okay? Yeah, well, I'm going to do it now. I'm going to convince you that this one is exactly the right one to do. Okay, here. Let's prove it. The variance, by definition, is what? It's this guy right here, right? So variance of the variable x is equal to the expected value. Okay, so how about I prove this thing for the continuous case? So by definition, this one is from negative infinity to infinity of x minus mu sub x right here, square f sub x of x dx. Right? Which is the same thing as, well, e right here, expected value of x minus mu sub x, the whole thing squared. Right? So far so good? I just use the definition of the variance. Right? And now I'm going to do this. Well, before, you know that whenever I want to compute the expected value of whatever the function in here is, the definition is what? The summation of xi times that function right there, right? So, well, let me just compute this out first. What is this? I square this. This is x squared, correct? Minus what?
2x mu.
2 mu times x. Okay, so there is little mu sub x right here, x. And then what else? Plus mu sub x right here squared. Agreed? Right? And now, I claim that the expected value is a linear operator. Is everybody familiar with what I mean by linear operator or linear transformation? Yes, no? What do I mean by linear operator? All right. Store this one aside for a minute. A linear operator. All right. All right. What do I mean by a linear operator? For example, a matrix addition or something like that is a linear operator. What do I mean by that? A linear transformation. It is linear if and only if you let this guy acting on the sum of two functions. It's the same thing as what? The sum of this. Right? Remember that? Give me something that is linear transformation, a linear operator. An example.
Shifting or grabbing.
Integration. I claim that the integration is a linear operator. What do I mean by that? Okay? So L right now is nothing but the integral. Right? Is everybody familiar with this kind of notation? So for example, when I say that L right here is an operator, what do I mean by that? For example, in this case, I claim that integration is an operator. Right? Where L acting on f is what? Whenever I give you a function f, you just integrate it. Alright? So that's an operator. Right? I claim that this thing right here is linear. What do I have to check? I have to check that L acting on f plus g right here, for example, is the same thing as LF plus LG. In other words, distribute out. Hence the term linear. Now, how do I prove this? Well, L right here is the integration operator. So what does that mean? Whenever I give you FG, you just have to integrate that sum right there. Right? Correct? And integration right here, by definition, is the same thing as f dx plus g dx. Agreed? Yeah? And then this thing right here is nothing but LF plus LG. Can you see that? Right? And by the way, there is nothing special about FG right here. I can multiply A multiply F by A and then G by B right here. It's still the same thing. Right? because then this one is A and this is B, and then I can put A up front and then B up front right here. I have A right here and B right there. Yep. Okay. So basically, all I'm saying is that if an operator is linear, what do I mean by that? Whatever that operator acting on the sum is just like the sum of the two operators. That's what I mean by linear. All right. In in everyday life, not everything is linear. Correct? You can have non-linear, a lot of things. So now, backtrack to this thing. I claim that the expected value is linear operator. Why? Because remember, the integral right there is you distribute it. Right? I just proved to you right there. Right? So the expected value right here, I can just calculate the expected value of x squared, agree? And then plus what? Plus this one, so I have minus 2 times the expected value of mu x times x plus the expected of mu x squared, agree? Yeah? And now, this one is expected of x squared. And then what is this? Minus, what is this thing? 2, remember mu is a number. I can bring it up front. So I have, what is this? Mu sub x times expected of x. Right? And then plus what? E mu sub x squared. But now, what is E sub x? E of x, the expected of x, is exactly mu x. So you have mu x times mu x is mu x squared. So you have minus 2 mu x squared plus
mu x squared.
Right? So therefore, can you see that this one is nothing but minus mu squared? Because the expected of mu x squared is exactly mu x squared. It's a number. Right? So therefore, this one is exactly that. Hence, I just proved to you that in practice, it's better to use this formula right there. Alright? So now we're going to use this definition right here to compute a whole bunch of them. Bernoulli. Okay, so how do I compute the expected value of the Bernoulli? Okay, look at the formula again. What is that? Remember that this one is, how do you say it, discrete. So I need to use this formula right here. Right? And Bernoulli has two outcomes, I equal to 0 and I equal to 1. Right? So I just have to sum over from 0 to 1. Is that clear? So what do I have? Let's write out the formula right here. The expected value of, well, now I'm going to calculate the variance. Variance of x, which is by definition is the expected value of x minus mu, so x right here, squared, right? Or it is the same thing as the summation over I right there of xi minus the mu sub x squared times f of x I. Yeah? Let's just copy down the formula right here. I didn't do anything yet. I haven't done anything yet. Just use that formula, right? And now, a minute ago, we compute the mu sub x, which is the, whatever you call it, the expected value for the Bernoulli function. What is that? Look at your notes. I'm sorry? It's p. Thank you. So therefore, can you see that this one right here is nothing but the sum of what? xi right here minus what? P, the whole thing squared, right? And now what is this thing? F of xi. Whatever that is, we wrote it down a minute ago. It's 1 minus something. Yeah, it's x to the, it's p to the x times 1 minus p to the 1 minus x, right? That's xi, right? That's the, whatever you call it, frequency function for the Bernoulli. So now you just have to sum them up. When I is 0, when xi is 0, what do you have? Minus p squared, right? And some right here, remember, xi right here, there are two outcomes. Xi is 0 or xi is 1, right? So therefore, you have xi is 0, this is minus p squared, and then what is 1? P raised to what? 0 multiplied by 1 minus p to the 1, thank you, plus 1. Xi is 1, so what do you have here? 1 minus p squared, and then p right here to the xi, which is 1, times 1 minus p to the 1 minus 1, which is 0. So what is that? This is just p squared times 1 minus p, right? And this thing is plus 1. 1 minus p squared times p. Right? That's the expected value. Not the expected, how do you say it? Variance for Bernoulli random variable. And when you take the square root of that guy, you obtain what? The standard deviation. Okay? Now, let's do another one. How about when your x is exponential? Now this guy is continuous, right? So you can either use this thing definition right here, or you can use this thing right here. I'm going to use this thing right here because it's much easier, right? So I'm going to use that. So now let's copy this down. What is this? Okay. How about I move this thing right here? Does it help? Not really. Right here. It's this thing. Expected value of x squared minus mu squared. Alright? So therefore the variance of x right here is going to be what? The formula written to me, the expected value of x squared, right? Minus what? Mu squared. Very good. Now we just have to use that formula. What is the expected value of x squared? Here. It's nothing but you do x squared times x of x dx. Can you see that? Right? So let's use that. This one is nothing but the integral. Since it's exponential, I might as well cut it from 0 to infinity. So we have 0 to infinity of what? Of x squared times what? Lambda e to the minus lambda x dx minus mu squared. What is mu squared, by the way? We just calculated it a minute ago for... Is it 1 over lambda?
Yeah.
Okay, good. So there it is. Right? So therefore, what is, this integral right here, I can just take out the lambda. I have integral from 0 to infinity of x e to the minus lambda x dx minus what? 1 over lambda, and then the whole thing squares is 1 over lambda squared. Well, don't ask me to do this integration again. This thing right here, you have to do integration by parts, probably 2 times. Right? X squared e to the minus lambda x dx, do integration by part 2 times. You have to get it to be something like this. This integral right here actually turns out to be 2 over lambda squared. And then you have minus 1 over lambda squared, so the variance is going to be 1 over lambda squared. That's the variance for the exponent distribution. So therefore, what is the standard deviation for exponential. 1 over lambda square root of x. That's it. Now, how about we compute this guy? X is a normal distribution. Okay? We want to compute the, how do you call it, expected value. So what is it? The variance is, by definition, you just have to integrate over negative infinity to infinity of what? X squared times whatever the density function is, which is what? 1 over square root of 2 pi times sigma, and then what else? E to the minus mu, x minus mu, square over 2 sigma square dx. You just have to integrate that guy. Right? Okay? Actually, you have to minus mu square as well. I'm sorry. Let's see if I want to use the formula. So now, let me show you how to do this. I'm not going to do this thing out all the way. It's going to take the whole half an hour probably to do this thing. So x squared right here, e to the minus x minus mu square over 2 sigma square dx minus mu square. Okay, so this is this. Now give me an argument, or give me an approach on how to handle the first integral right there. I'm going to change, how do you say it, variable, let z equal to x minus mu over sigma, for example. That will take care of the exponent, right? Then the exponent will be e to the minus z square over 2 or something like that, right? And now over here you have x squared. Remember that a minute ago I already showed you the problem where this one is x and not x squared, right? This is x, not x squared. You follow exactly the same approach right there. Replace x by whatever, z, sigma z plus mu, right? And then you have to do integration by parts 2 times together. That's how you do it. Alright? Don't get scared. I just want to tell you, I want you to understand the idea right here. Don't get lost in the calculation. Alright? This calculation, it might take me 10 pages to do it, but so what? If I am careful and if I have time, I will be able to do everything. There is nothing interesting about that. Alright? Actually, on the exam, if you notice your exam, a lot of you, I actually am not interested in your calculation, in your algebra at all. I'm sure that everybody can figure out what 2 plus 5 is. I'm not interested in that. I want you to see the idea. I want to see the ideas, how you approach the problem. So a lot of you, when you make some mistake algebra, I just say, be careful right here. Either I take 1 point off, or I don't take anything at all. Because it's obvious that, like, that's just a stupid mistake. I make that point all the time. I don't care about that. If you know where you're going, that's all I care about. So exactly, that's the idea how to do this problem. Alright? And if you have time, you can just go ahead and do it. We are like almost graduate students right here, I don't care about the algebra part. This is not about it. Alright, so now, I'm going to actually do things randomly now. So, for example, why don't I just do this thing? I give you this function. F of x equal to, let's say, 2x. Okay? X of x equal to 2x. And then let's say that x right here is between 0 and 1. Okay? I want you to compute the expected value for it, for that random variable. How do I do it? Expected value, okay? So what do I do? This is expected, not variance, right? And this is continuous, so that means that all I have to do is integrate of x times the function, right? Right? So therefore, because this thing right here is from 0 to 1, so therefore instead of doing from negative infinity to infinity, I may as well do it from 0 to 1, right? So I'm going to have 0 to 1 of what?
Of 2x.
Of x times 2x dx. Can you see that? Okay, so this thing right here will be 2 integral from 0 to 1 of x squared dx, right? And then what do you have right here? 2x to the third over 3. So what is that? It's just 2/3. That's the expected value, correct? And now, if I want you to compute also the what is the other guy? Variance. How do I compute that? The variance of x. Everybody, remember the formula is what? Is the integral. I might as well cut it from 0 to 1 of what? Of x squared times the function. So this is 2x dx, right? Minus the expected value, which is mu right here squared. Remember, mu is the expected value. So what is this? This is integral from 0 to 1 of what? 2x to the third dx minus what? 2/3 squared. Can you see that? Yeah, because the expected value is mu. So therefore, 2/3 squared. Okay. So whatever you get, you get. All right. A bunch of things right here. Now let's move on. Well, this is just a summary of what we've done so far. If you have a random variable x and you want to compute the expected value, well, if it is discrete, then you just sum fxi, but you multiply by xi, right? Oh, by the way, if you just sum f of xi, what do you get? I'm sorry? Yeah, but what do you get in that thing? I mean, like it's the CDF, right? Correct? And if you sum from the whole thing right there, you get exactly 1. Otherwise, if you stop at some point, it gives you CDF. Can you see the difference right now? Therefore, now if you sum xi times f of xi, that one is the expected value. All right? And likewise, right here you have x fx dx, right? If you integrate of fx dx over the whole interval, you're going to get 1 if it's a density function, right? And if you stop at some point, it's going to be the CDF. Now, if you multiply x fx dx, integrate that one is the expected value. And the variance right there is, I recommend that you use this thing right here, you know, because instead of using the other one, it's going to be best to use this thing. The variance.
Nguyen?
Yes. Go ahead.
This is Debbie from Salt Lake again.
Okay.
When we have on Chapter 4, Problem 1, and we're asking to, if you show that if a random variable is bounded, that is, the absolute value of x is less than m is less than infinity, that the expected value exists. I know we're supposed to go ahead and use the definition of the expected value.
Basically, you need to show that. Basically, you need to show that the expected value, that the integral is finite, right? Okay, so therefore the expected value exists. So now here,
What's that m?
m is just some number. If you are not comfortable, replace m by a billion. M is a fixed number. All right. So basically, what does that mean? It means right here that the random variable x right there is always bounded. Right? It could be huge, but it's a finite number. Right? If you are not comfortable with that number, m, replace it by 10 or a billion. So I can. It's a fixed number. So therefore, now the expected value is going to be what? Anybody? By definition, come on, look at it. Just a minute ago, I put it right here. Integral x fx dx. Where is it? There you go. Right? So therefore, this one is integral from negative infinity to infinity of what? X fx dx. Right? And now, they told me that You know, like x right here is outside x. It's gonna outside the how do you say it? M and M right there. The thing is going to be 0, right? So therefore, I just have to cut my integral down to from negative m to m. Of this is x f of x dx. Okay, so far so good, right? Because that's what they told me, right? The random variable right there is bounded. In other words, outside that one, the integral right here is going to be 0, right? So I have that. Now I need to show that that one is finite. Anybody dare to venture how to do it? Well, remember that they told me that x right here is always, absolute value of x is always less than m, correct? That's what they told me. So therefore, this integral right here, can I write this one right here? It is at most, x right here is at most m, correct? X cannot be bigger than m. So therefore, this thing is the same thing. That's integral from negative m to m of m times f of x dx. Agreed? Yeah? Right? Because x is always at most m. So therefore, this thing right here, right here, that means that x is from negative m to m. So it has more m right here. And now argue from the why this one is finite. Well, this one is just like equal to what? M, I can print outside integral from minus m to m of mx dx. Agreed? Yeah? And now, I want to show that this one is finite number. Give me an argument that why is it that this one is finite. I might as well ignore the constant m outside, right? If that integral from negative m to m of fx dx is finite, then multiply by m is going to be finite. Right? A billion times 10 billions, I don't care, it's still finite. Right? So therefore, the job right now is to show that the integral from minus m to m of fx dx is finite. Give me an argument, everybody. Remember, your f of x is a what? A continuous function. And if you integrate a continuous function over a bounded interval, what do you get? A number. Correct? It cannot be infinite. Yeah? Is that clear? I integrate a continuous function over a bounded interval. It got to be bounded. Yeah? Oh, why do you look at me like that? Come on, guys. Think about it like this. If I have a function f of x, right, it is continuous. And now, what do you know about a continuous function on a closed and bounded interval? It got to achieve a maximum and a minimum, correct? A continuous function on a closed bounded interval got to have a max or a min. So therefore, f of x right here can be at most some number. Let's say n, some capital N right there, right? And now you integrate minus m to m of that constant dx. You can just print that constant outside. So it's just like you n right here, integral from minus m to m of dx. And what is the integral from minus m to m of dx? At most 2m. And 2m times n, still finite. So is that clear? Right? So that's the spirit behind this problem. Okay. Very good. And now, where was I? I forgot. The expected value and variance. Okay. I have 5 minutes. Do I want to do this one or do I want to go on? Okay, no, I don't want to introduce some new material. Let's just...
You know what would
Yes?
be, Dr. Nguyen?
Yes?
Would be really cool is if you took an example on a random variable maybe, where there's actual numbers, and show how the expected value works. So maybe from the table.
From a table? Well,
From a
sure.
table, from even a coin table, maybe?
Well, what do you have right here? Okay, there is a very cool example, I think, in the book right here, but, well, I think it's like this. You play a roulette game, a game of roulette, right? So it means what? You have something like this, right? And then you're going to divide into some small intervals, right? So you are going to have number from 1 to, I think, what is roulette? 38?
Yeah.
1 to 38 number, and then 1, 0, and 1, 2, 0. Right? Okay? And now let's say that you're going to play a bet. Place a bet. Now, you know, like you say that if an odd number comes up, you're going to win $1. If not, you're going to lose $1. Okay, so it's a fair game. Win one or lose one. So now, what is the expected value of the game? All right. So that's what let X right here denote the events that you gain, your net gain. Okay, X right here denote your net gain. Okay, by that I mean X right here. If you get $1 right here, it's going to be what? With probability what? An odd. How many odd numbers are there? You have like 1 to 38. That's what? Actually 1 to 36 only. I'm sorry. Okay, roulette 1 to 36 and then 0 and double 0. So 38 outcomes together. So now, if an odd number comes up, you win $1, right? So how many chances are there for the odd number to come up? 1 over 18. Right? No? What is that? 18 over 38. I'm sorry, yes. Right? And now, if an even show up, you
Why
will
is it
$1.
38 now?
I'm sorry?
Why is it 38 if the other one was 36?
Because you have also 0 and double 0. That's wild card.
Got it, thanks.
Right? So, if an even number show up, then you lose $1. And what is the probability of an even number show up? It's going to be what? 20 over 38, because you have that here. Two of them. Right? I shouldn't say even number. I mean, if a not odd number show up, then you know, like you're going to lose $1. So now, what is the expected outcome? The expected value of X is what? Is 1 right here multiplied by the frequency function. 18 over 38 plus the other one is minus 1 right here multiplied by 20 over 38. Okay, and then you calculate this one, I think it gives you minus 1 over 19. So the expected outcome is that. You're going to lose. Okay? You're going to lose. Of course, because you know, like you have many more non-odd numbers. Right? So that's the expected outcome. Well, beside that, I don't prepare and I cannot pull anything out on top of my head. This example, I will search for some, you know, and then we can just do it. So now we still have like 4 or 5 more minutes. We will just compute the all the frequency function that we know so far, distribution function that we know so far. I'm sick of the geometric distribution right now because we did it a few times already. We haven't done Poisson yet. Let's do that yet. Poisson. Okay. So now, how do I find the expected value of the Poisson? And the variance as well, for that matter. Expected value. Poisson, is it discrete or continuous? It's discrete, right? So therefore, we just have to multiply by xi and sum them, right? So now, what is the Poisson distribution? Remind me again. The Poisson distribution is what? I think it's like lambda something.
over k factorial.
Yep. Something like that. So let's put it down right here. So this one is lambda to the k divided by k factorial times e to the minus lambda. Right? So now what do I have to do? That is the frequency function. I need to multiply by k and then sum over k. Right? Okay, so I'm going to multiply by k right here and then sum over k. And k right here start from 0 to infinity. So far so good? Now, let's compute this guy. Now this is looking, this e to the minus lambda is independent of everything. Can I bring that from? Yeah, let's do that. So I have e to the minus lambda out here, and then k equal to 0 to infinity of k divided by k factorial. What is that? K minus 1 factorial. So this is k minus 1 factorial. And this is what? Lambda to the k. Can anybody give me a suggestion on how to sum that nasty looking thing? Well, how about I write lambda to the k as lambda to the k minus 1 times lambda? Right? So that I can identify with the thing in the bottom. So I have e to the minus lambda right here, and then the sum right here is k equal to 0 to infinity of lambda times lambda to the k minus 1 divided by k minus 1 factorial. Yeah? I just split the thing up right there. Then now this thing is e to the minus lambda, summation k equal to 0 to infinity, and then the lambda, it's independent of everything. So therefore I'm going to move the lambda up front as well. Why not? And then this thing right here is just lambda, right? To the k minus 1 divided by k minus 1 factorial. So far so good? Yeah? Okay, so now what do I do? Make a substitution. Actually, can you see that this thing right here, I may as well start from k equal to this thing right here. I should say right here this k is 1. Start from 1. Why? Because k minus 1, when it's negative, it's not well defined, correct? So therefore, I might as well stop right here at 1. Yeah? Right? Correct? Because when k is negative, it's not defined. K minus 1 is not defined. Factorial. So I'm going to just write it like that, and now I'm going to make substitution. What is the substitution? Let k minus 1 equal to L, for example, and then you will see that this thing is nothing but what? Lambda e to the minus lambda, summation of what? Let's say L equal to 0 to infinity of lambda to the L over L factorial. Yeah? And then what is the definition of this thing? It's exactly e to the lambda. So you have lambda e to the minus lambda times e to the lambda. It gives you exactly lambda.
Can you move that up a bit, please?
All right. Okay, so for those of you who came in late, you know, I said the homework, you can just hand it in tomorrow night. That's we are not